Okay, everybody. The second talk in the afternoon is given by Professor Paul Wedrich from the University of Hamburg. The title is From Linear Homology to Topological Quantum Field Theories. Let's welcome.
Okay, I would like to start by thanking the organizers of ICDS and BIMSA, and especially Professor Yao for making this possible. So this talk is about started for me with a collaboration with Morrison and Walker. We wrote a paper about 6 years ago titled Invariance of Four Manifolds from Kovanov-Rosansky Homology, and I would like to thank the selection committee for this year's Frontiers of Science Award for selecting this paper for an award. Okay, so this was the starting point, and I want to use this opportunity to talk about this work and also how it fits into a bigger picture. The talk will have 3 parts, a bit of an introduction, then I will talk about link homology and TFT, which have already appeared in the title, and then I'd like to propose 4 different ways in which one can reach TQFTs from structures that appear in categorification. So, introduction. Already mentioned at this Congress were the Whitney-Reshetikhin-Turaev invariants of 3 manifolds, and maybe one of the highlights of the first 10 years of this field of quantum topology, which maybe started with the discovery of the Jones polynomial, was the interpretation of the Jones polynomial and related invariances coming from ribbon categories of quantum group representations. For example, Whitney-Reshetikhin-Turaev invariance of 3 manifolds associated to the quantum group of SL2 can be, in practice, computed as sums of colored Jones polynomials at certain roots of unity. So this would be one way in which we could access 3 manifolds invariance if we, for example, know how to compute Jones polynomials, which is something you can teach to high school students. Okay, the second ingredient here is that by now we know that much of quantum group representation theory can be categorified. So this was a huge topic and still continues to be a huge project before we heard about this today. And relevant here was this amazing insight of Kovanov that the Jones polynomial admits a categorification to a link homology theory. And not only the Jones polynomial, but also its colored versions and various other quantum link invariants. And now, here's a challenge, or somehow my reading of a very important problem, namely originating in the work of Crane and Professor Frankel, who's here in the audience, and Kovanov, namely how to use categorification to build manifold invariants, which have to satisfy 2 things on my to-do list, on my wish list. Namely, they should be algebraically computable, for example, in terms of link homology. Just like the Whitney-Reshetikhin-Turaev invariants are computable from colored link polynomials. And second, ideally, they should be useful invariants for smooth 4-manifold topology. So I understand that this was one of the initial motivations of the categorification program. Okay, and the approach that I would like to entertain in this talk goes like this. So first, I want you to try to understand the background of this Whitney-Reshetikhin-Turaev invariance in terms of extended topological quantum field theories. And there's not one of them, there are actually several, and I will come to that. And some of these TQFTs are extended and in some sense local. They're determined by local data of an algebra categorical nature. And then one idea would be to take this local data that controls the WRT invariance to categorify it. And categorification is typically not a deterministic process, it's more like an art, and sometimes we have different choices of how to do this. And then we can take this categorified local data and try to reassemble it into TQFTs. And the results that we'll get will depend on the choices that we made in the categorification. And we might see that categorification may circumvent some of the finiteness constraints that appear in WRT invariants. For example, that we have to go to a root of unity or that we have to semi-simplify. Okay, so today I want to I want you to take away two things. The first is that there exists a first approximation to a solution of this problem. This is what this paper with Morrison and Walker is about. So there exists a family of invariants which are computable in terms of link homology theory, and they turn out to be able to say something about smooth four-manifold topology. And the second thing is that there seems to be a second generation of such invariants, which are even a bit closer to categorifying WRT invariants. Okay, so that was the introduction, and now I would like to give a brief outline of what I mean by link homology and TQFT. So let's start with a link polynomial. So if you want to provide a link polynomial in a generators and relations kind of way, what you can do is you can model links that are embedded in R3 by their diagrams that you get by a generic projection onto a plane. And then to give a link polynomial, we have to assign polynomials to these diagrams, and then we have to convince ourselves that the result that we'll get does not depend on the diagram, but only on the underlying link. And so we have to check that the evaluation remains constant under performing Reidemeister moves. A link homology theory is a categorification in the following sense. So to a link diagram, one associates typically a chain complex. You have graded vector spaces, so that the graded Euler characteristic of that chain complex recovers the polynomial link invariant. And now this lives one categorical level higher, so there is the opportunity to also say something about surfaces embedded in four manifold and not just about links embedded in three manifolds. And one way of encapsulating this is to consider a category where the objects are links embedded in R3 and the morphisms are link boardisms embedded in four-dimensional space which connect two links, and then these can be considered up to isotopy, rel boundary. And ideally, one would like to define a functor out of this link and link boardism category to chain complexes of vector spaces with the property that the Euler characteristic of the chain complexes recovers the polynomial. And there's a generators and relations way of doing this, namely to every link diagram you assign a chain complex, to every elementary transition between link diagrams you assign an elementary chain map, and then one level higher there's some moves that have to be checked, which are the higher dimensional analog of Reidemeister moves, and here are some examples. So for example, if you have four strands which cross in a single quadruple point, you can perturb this. You see tangle diagrams, there are 9 steps in the top line. They're all related by Reidemeister 3 moves, but it's a non-trivial loop of Reidemeister 3 moves that represents a boardism which is isotopic to the identity boardism, and so the associated chain map in the link homology theory ought better to be homotopic to the identity. And this is the type of relations one has to check if one builds one of these link homology theories by hand. And so this has been done in various contexts, and I mentioned one work with Erik and Tubenhauer, where we proved that a version of the GLN Hovanov-Rosansky link homologies, which is accessed via combinatorial formalism of forms due to Robert and Wagner, indeed provides a link homology theory that fits into this framework, and they give categorifications of the GLN Reshetik and Toraev invariants, and if you set n equals to 2, you get the Jones polynomial. Okay, what about TQFTs? So this is a very broad concept. The slogan would be one studies representation theory of manifolds organized into boardism categories. So in some sense, it's also some kind of representation theory. Let's say it's an assignment of algebra categorical structures to space-times, which is in some sense compatible with gluing. So let's fix a spatial dimension n, and secretly we should also fix a tangential structure. For me, all manifolds will be smooth and oriented in this talk. And then to such n-dimensional manifolds, one wants to assign some algebraic structures, and then typically one is not satisfied, but one wants to either go up in dimension or down. So for example, we could ask that this construction is functorial under certain n+1 dimensional boardisms, Or we could ask whether this theory can be extended downwards. And then the yoga goes like this, that whenever you want to assign something to lower dimensional manifolds, the corresponding algebraic invariant has to be one categorical dimension higher. And this is especially useful if you want to be able to glue your invariants across some part of the boundary. Yeah, if you get such a thing, then you have manifold invariants that can be computed via cut and paste techniques. So imagine you have a complicated manifold, you cut it along some hyperplane or even some lower dimensional submanifolds into manifolds with corners. You assign algebraic invariants to these then easier pieces, and then you algebraically reassemble them to compute the complicated manifold invariant. That's at least the idea. And I want to use the terminology that a TQFT is local if it extends down to the point, so as far down as possible, and then all values are essentially determined by what this invariant of the point is, together with the gluing formalism. Okay, and so if we're very, very lucky, then the best case scenario for such a local n+1 dimensional TQFT would say assign vector spaces to closed n manifolds. It would assign scalars to closed n+1 manifolds because they will be bordisms from the empty n manifold to the empty n manifold. And the empty n manifold gets assigned the one-dimensional vector space. And then we could extend down and we would assign linear categories to n-1 manifolds, and you could go down, 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 and so on. And the dimensions have to be complementary, so that at the level of 0 manifolds, one has to assign a certain type of n category. Okay, so this sketch here ignores many important aspects. So for example, one should be very careful about where all of these n categories or k categories live. So they should live in some ambient symmetric monoidal higher category. I have not said anything about the values of such a TFT on manifolds with boundary, only about closed manifolds here. And I've completely ignored questions of dualizability, including the strong finiteness conditions that are necessary to go to this top dimension n+1. And I've completely ignored pivotality aspects, so requirements on tangential structures of the manifolds that get fed into this construction. Okay, but so to warm up and to put the categorified things that I want to talk about later into context, I want to go through a case study of 3 really well-known and well-studied families of topological quantum field theories. And the first one is I like to call the Turaf-Virol type local TFTs. And they are TFTs in 2+1 dimensions. So they assign vector spaces to 2 manifolds and scalars to 3 manifolds. And let's go through. So I added some fine print that I probably won't be able to get into, but so this is, this is a very celebrated research area. There's lots of works, and it's absolutely hopeless to be able to cover this in such a talk. So on the top level, we get the numerical Turaf-Virol invariance for 3 manifolds. Fine. The construction can be done starting from a spherical fusion category, which can be interpreted as a thing that gets assigned to the point here. And then there are interpretations for the intermediate levels of this TFT as some kind of skein modules in a similar way as they appeared in Pang Shang's talk yesterday evening. So associated to such a spherical fusion category is a graphical calculus of string diagrams in the plane, or in the spherical case, even on the 2-sphere. And so, for example, to a surface, one can assign a skein module of string diagrams of graphical calculus of that spherical fusion category drawn on the surface itself. Okay, good. Next up is the Crane-Jeter type of TFTs. This is 1 dimension up. It's also a local TFT, in this time 3+1 dimensions. The top dimensional invariants are defined on closed 4 manifolds, and the scale is called the Crane-Jeter invariance. This construction starts based, for example, on a ribbon fusion category. That is a special type of braided monoidal category. Earlier we had a special kind of monoidal category. So you see also the algebraic input is 1 dimension higher. And then as before, the intermediate layers in this TFT can be described in some sort of a skein theory. So here, for example, to a three-manifold, closed three-manifold, one would assign a vector space, which can be described as a skein module of ribbon graphs embedded in the three-manifold, where all the edges and the vertices are labeled by data that comes from this ribbon fusion category C. Okay, and now this is a four-manifold invariant, but unfortunately it turns out to be not extremely interesting because for a closed four-manifold it only depends on Euler characteristic and signature, so classical invariance, and it won't say anything about smooth structure, say. Okay, and then now we come to the Whitney-Reshetikhin Turaev invariants, which are a bit more exotic, but there's a question. Yeah, you can also do something there, and I didn't want to get into it, yes. Yeah, so you could describe skein 2 categories. Yeah. Okay, so here's the slightly more exotic example, namely the Reshetikhin Turaev TFT, which at first sight does not look like a local TFT. So this also assigns, like the Turaev-Vero theory, scalars to three manifolds, vector spaces to two manifolds, and certain categories to one manifold. The scalars are known as WRT invariants, and the construction, in some sense, depends on the modular fusion category, which here can be interpreted as being assigned to the circle. So here's this caveat. This does not immediately look like a local TFT, but it can be naturally interpreted as a boundary theory for this Crane-Yetta local TFT. And so this idea of boundary theories is some extremely useful concept. And in some sense, this even leads to interpretations of quantum field theories as being representations for topological field theories in one dimension higher. But here everything is topological. Okay, and so this idea of a boundary theory can be exemplified in a concrete example. So when we compute Whitney-Reshetikhin Turaev invariants, for example, as sums of Color-Jones polynomials, secretly what is happening is that we write the three manifold as the end of a surgery cobordism from the empty manifold. So we write the three manifold as the boundary of a certain type of four manifold. And we can think about the four manifold as a bordism from the three manifold to the empty manifold. And now the Crane-Yetta TFT will assign a linear map from the skein module of the three manifold to the skein module of the empty manifold, but that's just the scalars. And so we can feed in a distinguished skein into this linear map and evaluate it to get a scalar. And the distinguished skein is the vacuum. It's just the empty string diagram in the three manifold. And then it turns out that the result does not really depend on what the four manifold was, only depends on Euler characteristic and signature, which can easily be renormalized, and therefore one obtains a three manifold invariant at the boundary. So this computational mechanism for computing WRT invariants via Kirby coloring a surgery link, this already shows some aspects of the Reshetikhin Turaev theory being a boundary theory for the Crane-Yetta theory. Okay, so that's, there's one more relationship that I wanted to mention, namely, so all of these three case study TFTs that I have here can be constructed from the representation theory of quantum groups, from the ribbon category of representations. That's a certain type of braided monoidal category, but I could also forget the braiding and just treat it as a monoidal category. And then one can compare the Turaev-Vero invariants and the Reshetikhin Turaev invariants, and one finds this relationship that the Turaev-Vero invariant is norm square of the Reshetikhin Turaev invariant, which somehow comes from taking the three manifold, thickening it by an interval, and then on the one hand, one computes the Turaev-Vero theory for the sandwich, or one looks at the boundary of a three manifold times interval, and one gets two copies with different orientation of the Reshetikhin Turaev invariant. So that might appear later on and might appear categorified. Okay, so takeaways of this case study is that quantum group representation theory not just yields one TQFT, but a triple, a local three-dimensional theory, Turaev-Vero, a local four-dimensional theory, Crane-Yetta, and maybe not local, but still extended 1 to 3-dimensional Reshetikhin derived TFT. The top-dimensional invariants in the derived zero in the Grignetta theory need some strong finiteness conditions. Typically, one works at a root of unity and performs some semi-simplification. But the lower dimensional strata of this TQFT, of this family of TQFTs, seem to be more robust because they can be described in terms of skein theory and they don't require going to root of unity or semi-simplifying. And then they fit into this framework of local n plus epsilon dimensional TQFT. So they might be partially defined. This is a concept that I learned from Kevin Walker. And the epsilon here indicates that to an n manifold you assign something like a vector space. Diffeomorphisms of these n manifolds still act by automorphisms. You might see some aspects of some n plus 1 dimensional TQFT in there, but it's not required, and it still makes sense as a TFT. One takeaway that we can also reach here is that if one wants to categorify Reshetikhin derived invariants, the Reshetikhin derived TFT, then maybe it's a good idea to first try to categorify the Grignetta and the derived zero TFTs because they're local. They're somehow determined by local data. The strategy that went into the paper that I'm talking about is that categorification and skein theory should together give access to categorified versions of Grignetta invariants in all but the top dimension. So this would be between dimensions 0 and 4. And categorifications of the derived zero type TFTs should give invariants up to dimension 3. Yep. Okay. Good. Where is this all coming from? So here is the periodic table of higher monoidal n categories, or if you want, the periodic table of n plus epsilon dimensional TQFTs. Versions of this table have appeared around the same time as the famous cobordism hypothesis of Weierstolen, and then a sketch proof by Lurie. And the local data for this local TFTs can be organized here. And so how to read this table is like this. So in the columns are parameterized by categorical dimension. So for example, in the column 1, you have 1 categories, monoidal 1 categories, braided 1 categories, and so on. In column 2, you have 2 categories, monoidal 2 categories, braided 2 categories, and so on. So, and the rows are then parameterized by somehow level of monoidality. The first row, the E1 row, contains algebras in sets, categories, 2 categories, so monoidal things. The second row contains braided algebras, so commutative monoids, braided monoidal categories, braided monoidal 2 categories, and so on. The dimension of the associated TFTs is computed using the following formula. You take the category level, so the column index, and the degree of monoidality, which is the row index, and you add them. So for example, monoidal categories, there you have 1 plus 1, so you have 2 plus epsilon dimensional TQFTs, for example, the derived zero type. 1 down, you see braided categories. Those are E2 monoidal 1 categories. 2 plus 1 is 3, so you get 3 plus epsilon dimensional TFTs. Okay. The manifold invariants that I want to reach are of the type that they're skein modules. And this table also parameterizes what sort of skeins one should be looking for. So we're quite familiar that in the level of monoidal categories, we have string diagrams which are modeled on lines in the plane, so lines in 2D. In the case of braided categories, we have lines in 3D that can tangle and braid. And for me, categorification is a process that goes 1 step right in this table, which replaces sets by categories, categories by 2 categories, and so on. So looking for categorified versions of these TFTs, I would look 1 step to the right from the famous places here and work with surfaces in 3 manifolds and surfaces in 4 manifolds. So it turns out in this discrete setting that I've been discussing of locally linear things, there's some stabilization. As soon as you have high enough monoidality, everything becomes symmetric monoidal. this is a bit of an artifact here. Yes. Okay, so now, are there any questions before I go to the categorified story? Okay, doesn't seem to be the case. So, the derived Viro TFT and the Crane-Yetta TFT I wanted to interpret as local TFTs, so they come from local data that fits in the table, namely monoidal categories and braided monoidal categories. And now I want to use categorification to get categorified local data. I want to step 1, click to the right in the table, and I'm looking for locally linear 2 categories of the monoidal and the braided monoidal kind. So I'm talking about 4 different versions here. The first one I like to call the Asaeda-Frohman-Kaiser type TFTs. They're based on skein modules whose skeins are surfaces in 3 manifolds. Another thing that could be put here are the Douglas-Reuter TFTs. So they're fully extended 4-dimensional TFTs based on the concept of fusion 2 categories. And the 3 plus epsilon dimensional part of those can be described via skein theory of certain types of foams, so generalization of surfaces in 3D. And they're extremely interesting. They have an extension up to 4D using state sum constructions. However, they have some inbuilt semi-simplicity, so they might not detect exotica in the oriented case. The one step down in the table here, in the braided 2 category slot, are invariants that we've constructed in this paper with Morrison and Walker. So they're skein modules of surfaces in 4 dimensions, where the skein relations are coming from a link homology theory. In this case, concretely, the GLN Kovanov-Rosansky link homologies. And then, when one works with link homology theories, the invariants are typically computed as homologies of chain complexes. And one can ask if a similar construction can be performed without computing the homology of these chain complexes, but rather to work with the chain complexes themselves. So then one is not in the realm of locally linear braided 2 categories, but locally stable infinity 2 categories, equipped with an E2 structure. For me, that's somehow a different category, so a different type of TFT. And the first steps into the direction of such TFTs have taken a joint paper with Leon Leo, Aaron Maisel-G, David Reuter, and Katharina Stroppel last year, where we built a prototypical example of such a braided infinity 2 category, starting from Rouquier complexes of circle bimodules. And the idea is that this and its quotients should lead to some sort of a derived skein module of surfaces in 4D. And then there's something else one can do. One can forget about the braiding, just treat this as a monoidal infinity 2 category, and build derived skein modules of surfaces in 3D. And that's something that we started to study last year in collaboration with Matt Hogenkamp and David Rose. And in this theory, we see some relations to derived Viro and Reshetik and Turaev categorification very explicitly, and at the end of the talk, I will come back to this. So these are the 4 types of TFTs. So they're sorted, so they fit into this table, and they want to be interpreted as categorifications of the derived Viro local TFT, or the Crane-Yetta local TFT, and what is different between them is whether the local algebraic data is interpreted in a discrete way as a locally linear type of higher category, or as a chain complex enriched as a locally stable infinity 2 category. Okay, so I'll say a little bit about each of these 4 entries. So maybe first about the Asaeda-Frohman-Kaiser TFTs. So they start with a locally linear monoidal 2 category. And in some sense, when Kovanov constructed his famous categorification of the Jones polynomial, there was quickly an extension to tangle invariance. And everything that was done there seems to be built on such a locally linear monoidal 2 category. And maybe the easiest way I know how to get such an interesting example of such a locally linear monoidal 2 category is to start with a commutative Frobenius algebra that corresponds to plain old two-dimensional TQFT, and then look at the linearization of the space of embedded two manifolds in the three manifolds, and impose local relations that are in the kernel of that two-dimensional TFT. And in the case of Khovanov homology, there's a famous mnemonic for this type of thing. Somehow you look at the Skane module of surfaces in the three manifold, the manifolds, the two manifolds, the surfaces are allowed to carry dots. And then you impose some local relations that the sphere is 0, a dotted sphere is 1, there's a neck cutting relation, and if you have more than 2 dots on this piece of surface, it's 0. So that gives, yeah. There's an interpretation of the dots. If 2 is invertible, a dot is half a handle, which you can see from this neck cutting relation. Anyway, it's some local data. You know, if you do the graphical calculus for ribbon categories, you typically have strings which meet in vertices, and the vertices are actually coupons, and the coupons are labeled by certain morphisms. So here, instead of coupons, you have dots. That's roughly what's going on. Okay, so this Khovanov-Barnard-Skane theory is, for me, as fundamental for this type of story as the Temperley-Lieb graphical calculus is for the Jones polynomial. In fact, this locally linear monoidal 2 category built on these Skane relations gives a categorification of the Temperley-Lieb calculus. Okay, but there are more general things one can do, and what one builds from this is to every three manifold, one assigns a Skane module with Skanes given by decorated surfaces or forms that are embedded and considered up to local relations. And then one can extend this down in dimension to surfaces. One can assign linear categories whose morphism spaces are computed from values of this TFT on surface times interval. And these linear categories have been used, for example, to construct Khovanov homology of links in thickened surfaces by Berner, and their categorification of Temperley-Lieb Skane modules for surfaces, and maybe even the Skane algebras that appeared in Pangshang's talk yesterday evening. So much for as a warm-up. Now let me get to the work with Morrison and Walker that started this for me. So here the local data that is assigned to the point is a locally linear braided monoidal 2 category that we extract from a link homology theory, but the link homology theory has to satisfy certain things. So it has to be functorial for link cobordisms in 3-ball times interval. It has to be E3 monoidal. That means it somehow sends disjoint union of links to tensor product of chain complexes, and it has to satisfy a certain 3-sphericality condition, which means that the link homology secretly is also well defined for links in the 3-sphere. And there was one technical thing that was missing to run this construction, and it had been missing for about 10 years, and that is a certain type of additional movie move that the link homology has to satisfy. And so this is the so-called sweep around move. It is, imagine in this little picture T, there's a 1-1 tangle, so cut open not a link, and then it has a jumping rope, and it jumps once like this, and it turns out that this traces out a link cobordism, which in R3 is not isotopic to the identity. But if the link lives in S3, then this is isotopic to the identity through some isotopy of link bordisms that basically goes through the added point at infinity. And so basically we had to prove this type of movie move for link homologies before being able to run the construction. And the problem about this move is that it's a non-local move from the perspective of R3 or from the perspective of link diagrams. So there's an infinite family of them, and one has to be a bit careful how to even prove this. Okay, but we did it, and that let us run the construction. And so the idea is to a 4-manifold, you assign a Skane module whose Skanes are decorated surfaces in the 4-manifold. Concretely, they're surfaces in 4-manifold with some interior balls removed, and then where the interior balls are removed, the surface can end in certain links. The links then live in 3 spheres, and they have to be decorated. They're somehow the coupons in this theory, and they have to be labeled by elements of the link homology of that link that appears on the inside. And then there's a kind of Skane relation that lets you remove a larger ball from the 4-manifold and update the label that appears on the boundary. So these are the type of skein relations that we consider, and by now there are other versions of this construction. For example, one by Darren Chen, which starts with linked Floer homology and runs a similar construction, but it requires different skeins and different skein relations. Now, this theory extends down, and so for example, for 3 manifolds, you get linear categories with morphism spaces that are computed from the invariant of the 4 manifold, 3 manifold times interval. And if you want to recover the link homology theory, you can now do so by evaluating the 4 manifold invariant on the 4 ball with the link given as a boundary condition. So in some sense, to even get at this invariant, there's a bit of a paradigm change happening, namely, the link homology is not considered as a 3-dimensional gadget. It's not an invariant of a link in 3 space. It's an invariant of the link sitting on the boundary of the 4 ball of some concrete 4-dimensional space. Okay, and so maybe let me say a bit about the definition. So a nice thing about skein theoretic invariants is that they're manifestly intrinsic. They're coordinate free. You don't need to choose any projections. You don't need to use any data structure. It's just the space of all skeins embedded in the manifold, linearized up to local relations. So it's somehow intrinsically defined. You just have to specify a reasonable set of skein relations. What can happen, and I interpret Professor Lustig's talk as warning us about this, that sometimes when it's a very infinite object, and depending on how good your skein relations are, it could happen that the space stays infinite, or it could become very small. But in any case, it's somehow an intrinsic definition. So then a problem is, how is one ever going to compute the answers? How does one actually algebraically access these types of skein modules? And a year later, there was a very surprising paper by Manolescu and Gibran Manolescu and Ikshir Nathaler, which showed that for 4-dimensional 2-handled bodies, there really exists an algebraic description of these skein modules. And then in joint work with Manolescu and Walker, we extended this description, and which now lets us, in principle, compute these skein modules for an arbitrary 4-manifold, compact, oriented, smooth 4-manifold, based on a handle decomposition. And the idea is you first remove the 4 handles. That doesn't do anything to the skein modules, they're isomorphic. Then you remove 3 handles, 2 handles, 1 handles, until you're left at 0 handles. That's a disjoint union of 4 balls. And for them, you have a link homology way of computing this. And so in principle, this says that these skein modules, given a handle decomposition, can be reduced to a link homology computation in the 3-sphere. So the skein modules can be reduced to that case. Okay, and then with Hogenkamp and Rose, we got to an even more concrete description of these skein modules based on Kovanov homology for 4-dimensional 2-handle bodies, or more precisely, the result of attaching 2 handles to the 4-ball. And there, the skein modules can be written as an explicit co-limit of colored Kovanov homologies of the attaching link of the 2 handles. And very concretely, this can be interpreted as a large color limit of the colored Kovanov homology of the attaching link. So it really rhymes with the surgery description of the Witten-Reshetik and Toraev invariants. And 2 copies of the natural numbers per handle. Yeah, so it's basically parallel cables of the attaching knot for each handle, and then for the SL2 story, you have somehow an even part and an odd part, which corresponds to the second homology of the 4-manifold with Z-mod 2 coefficients. And if you do a GLN, then it will be, yeah, mod n coefficients. So yes, I mean this in principle computability following a handle decomposition, and then well, it turns out that different indices of handles are differently computable. So it turns out 4 handles are trivial, 3 handles are okay, 2 handles are governed by this formula of Manolescu and Nathaler, One handles are pretty hard still. No, but I'm happy to give you one after the talk. Yeah. Sorry. Okay. Fine. So, but that somehow reaches one item on the wish list, that this is in principle reducible to a link invariant computation. Okay. And now sometimes, so okay. Now it can happen that the skein module just vanishes. And there's a very cool result of Ian Sullivan and Melissa Zhang that shows that the skein module based on Hovanov homology for S2 times S2 vanishes. So that's a pretty drastic collapse. If you think about what the skein module is, it's somehow a linear combination of embedded skeins in the four-manifold modulo local relations. You always have a vacuum skein, which is just the empty diagram. And if the skein module vanishes, that somehow says that the relations, the local relations embedded in this manifold become inconsistent. The vacuum is not linearly independent anymore. It's just equal to 0. So now that might be disappointing if this theory collapses completely if compactified on S2 times S2, but it actually got us quite excited. And the reason is that these skein modules are really well behaved under disjoint union, connect sum, and boundary connect sum. When working over a field, it's really multiplicative. If you have a connect sum of two four manifolds, the skein module, when computed over a field, is just isomorphic to the tensor product of the two skein modules of the summons. Now, it's known that TFTs that are multiplicative under connect sum in 4 dimensions do not have a chance to detect exotic smooth structures if connect summing with S2 times S2 behaves invertibly, because then you can at most get an invariant up to stable diffeomorphism. But if the invariant of S2 times S2 vanishes, then connect summing with S2 times S2 will not behave in an invertible way. So that happened early last year. Another thing one can do, and this is something that's well explored in the case of link homology theory, is to look at deformations. And there's a representation theoretic interpretation. So if you start with a link homology theory based on GLN, there's a way of deforming it to a link homology theory associated to a Levy subalgebra. So for example, direct sum of GLNIs, where the Ni is sum to N. Famous example is when you start with Hovanov homology, which I associate to GL2, you can deform it into GL1 plus GL1. Each of these link homology theories for GL1 is trivial, but the deformation is interesting, and it gives rise to Rasmussen's S invariant, which is a lower bound on the sliced genus, and was one of the first applications of link homology theory to four-dimensional topology. And in this paper with Morrison and Walker, we study deformations of the skein modules associated to these deformations, and we obtain numerical invariants for smooth surfaces in four manifolds, which happen to be lower bounds on the genus, and they can be interpreted as generalizations of Rasmussen's S invariant. These genus bounds have also independently been considered by Wren and Willis, and based on very cool work of Chuyu Ren the year before, which was about the Rasmussen S invariant of torus knots, they were able to control how these S invariants behave, for example, under two-handle attachments. And they did a very detailed study of these S invariants for surfaces in the Kovanov case, and they managed to prove certain vanishing results for skein modules, and on the other hand, also non-vanishing results. And then they were able to show that the skein modules, but also the associated S invariants, are able to distinguish exotic pairs of four manifolds. And in some sense, this can be, so this is in some sense a skein theoretic tool, an algebraic tool that can detect exotic smooth structures. It's maybe the first algebraic gadget that does this. Okay, so I put a check mark at application, so at least this sort of technology is ripe for applications in smooth four-manifold topology. But maybe let's go back to the original motivation, which was maybe to categorify WRT invariants. And it turns out that these skein modules do not categorify WRG invariants. So, in some sense, in their paper, in the Wren-Willis paper, they distinguish exotic pairs that were not distinguished using gauge theory, as far as I understand. But your question now was about new invariants for 3 manifolds? For 4 manifolds? Yeah, these. Yes, yes, these. Okay, great. Okay, so an outcome of this paper that showed that in principle these gain modules are computable was that we found one 4 manifold with a certain boundary condition where the skein module is badly infinite dimensional. That also means you cannot decategorify it by taking its dimension because the dimension will not be a number. And so in some sense, these skein modules do not have a decategorification. It's an open problem to decide when these skein modules are finite dimensional in each degree and when not, so that we have examples of both cases. So they're not categorifications of anything. They're built from categorification, but they don't categorify something themselves. And the example that we had was take the 3-ball times a circle, and the link in the boundary is 4 points in the 4-ball times a circle. Now, the skein module can be interpreted as the zeroth Hochschild homology of the category that this TFT assigns to the 3-ball with 4 boundary points. And every rational tangle with 4 endpoints will give an object in that category that has an identity morphism, which is the Bordism from this tangle to itself. And if you trace it, you get a rotation surface spanned by this rational tangle. So we compute that these rotation surfaces are linearly independent skeins, and they live in degree 0, and there are infinitely many such 4-ended tangles. So you have kind of an infinite dimensional space in degree 0. And it's kind of instructive to see what goes wrong in this here to cause this infinite dimensionality, because in Kovanov homology, we're used to assigning to these rational tangles some chain complexes over some additive category. And this category is somehow very small. It's generated by 2 objects, 2 resolutions that you know from Kovanov's cube of resolution. And so in some sense, you would expect that if you take the trace, a complex should decategorify to its Euler characteristic, and that should be generated by the traces of these 2 objects, the 2 resolutions. But here it doesn't happen. And a reason for this is that we have taken link homology very early. And maybe this would not happen if we instead work with a chain complex. And yeah, a possible remedy would be to run the entire construction based on the Kovanov chain complexes instead of the Kovanov homology. And in this particular example, we can actually do this. Yeah, we can compute Hochschild chains for this DG category that Kovanov uses. So, in this case, we would compute the Hochschild homology of Kovanov's arc rings. And that gives an answer that is locally finite dimensional. So it remedies this problem. In fact, if one does this, one recovers Rosansky's Kovanov homology for links in S2 times S1, so a known invariant. So that motivates going to this chain complex version, this infinity categorical way, locally stable infinity 2 categorical way of accessing similar kinds of invariants. So here, so this is the 3rd type of TFT that I'm talking about. The local data is, again, something like a braided monoidal 2 category, but it will live in this fancy homological algebra land of locally stable E2 monoidal infinity 2 categories. This should be constructed from the chain complexes that one uses in link homology already. But this object should be considered as an object of some symmetric monoidal infinity 5 category that we still have to define. It should be 4 dualizable in there, and it should be equipped with an S of 4 homotopy fixed point structure so that it has a chance to give a 4-dimensional TFT in that kind. So first work in this direction builds an object that is getting in this direction. So we build a locally stable E2 monoidal infinity 2 category whose braiding is given by Rouquier complexes of circle bimodules. This is a step along the way to supplying this local data. it's not quite there yet because the objects in this category are not dualizable, which is related to this old problem that triply graded homology is typically defined via grade representatives of links, and you cannot treat tangle invariants directly. There's a nice side remark that I can make here. So in recent work with Tobias Dickerhoff, which is inspired by work of Kapranov and Schechtman that we've maybe heard about this week already, and earlier work of Rina Anno, we found that this braiding on this infinity 2 category of circle prime modules with the Rouquier braiding comes from a factorizing family of Pervers-Schobers and symmetric products of the complex line. So there's this beautiful work of Kapranov and Schechtman which classifies perverse sheaves on that space in terms of a natural number graded bialgebra object. And we found that singular circle bimodules lead to direct categorification, and therefore an explanation of where this Rouquier braiding comes from. Okay, this is the start of a project here. There are lots of challenges involved in this. So first we want to go to a GLN version. In some sense, at the moment we're at this triply graded setting associated with GL infinity in some sense. We want to go to a GLN version where we can hope that this category is generated by 2 dualizable objects and sufficiently pivotal once we have this. And then the next challenge is that once this local data exists, we have to globalize. We have to have a mechanism which is now fancier than just writing down a skein module, which goes from that local data and it computes the invariance of more complicated manifolds. And this is related to Wedrich factorization homology developed, amongst others, by John Francis, who's here in the audience. Okay, and while this is going on, we also wanted to do something easier. Namely, we wanted to forget about the braiding, which is causing a lot of the complexity in this story, and provide a sort of a categorification of the derived zero TFT using the same types of ideas. And so this feels very similar in categorical level to bordered suture Tegart-Fleur homology. And what it would do is it would assign chain complexes, or in some sense derived skein modules to 3 manifolds, and to surfaces it would assign DG categories, whose morphism spaces can again be computed from the 3 manifold invariant. And here's the catch. The local data is the old local data of this Assaida Frohman Kaiser TFT. So it's these locally linear monoidal 2 categories that can be constructed very easily. And so it's completely governed by skein theory in the 3-ball. Yet there's a difference because the complexity, this derived structure, comes from performing all the gluing operations in a derived way. So every connected 3-manifold arising from gluing a bunch of 3-dimensional balls along part of the boundary, and when we perform this, this gluing should be modeled as some kind of derived tensor product over the DG categories associated to the surfaces where we're gluing over. And basically, starting at the 3-ball, if one just thinks about that all these self-gluing operations should be performed as derived tensor products and not just ordinary tensor products, one ends up with kind of an ad hoc description of a derived skein module. It turns out that this can be done in some non-circular way, also for the surfaces. And I'll finish by mentioning a result from last year by Hogan and Rose in joint work. So for every marked surface, so these are 2-dimensional one-handle bodies, we can associate a DG category that's canonically associated to the surface. Its homotopy category is what the Assaida Frohman Kaiser TFT would assign to it, and its Grothendieck group is the Temperley-Lieb skein module of the surface, can be computed from any handle decomposition. It carries a coherent action of the orientation-preserving diffeomorphism group. The graded Hom complexes have locally finite-dimensional cohomology, and they're related to these Wyszynski-Willis invariants. And the cool thing is that the Hom pairing categorifies the natural Hermitian pairings that appear in the derived zero cranietta and Rishitikin derived construction associated to the surface. And here's this nice thing that in categorification we have Q interpreted as a grading. And here one computes somehow the Euler characteristic of a Hom space, and the Hermitian here translates into the sesquilinearity of the grading shift in the Hom pairing. Okay, and then there's something about generation that also has a nice interpretation, but I'll come to a summary. So we started interpreting Reshetik and Turaev as a boundary theory of Crane-Jeter, and as a square root of the Turaev-Viro theory, and this can guide categorification. The lower dimensional levels of these TFTs should be accessible using skein theory or derived skein theory. We start to see two candidates of categorified Crane-Jeter and categorified Turaev-Viro each, one's in the linear setting and one's in the stable setting. They fall into two generations. These linear skein theories, they are by now somewhat computable. They're ready for applications in smooth phone manifold topology, and they're sensitive to exotic smooth structures. And the second generation is somehow related to derived skein theories. We expect better decategorification behavior, but they're very challenging technically, and they need expertise from many directions. So I'm very happy that I was able to talk about this topic here and interact with many people. Thanks.
Thank you, Professor Wedrich. Any questions?
So by derived skein theory, do you mean like if you consider non-derived skein, usual skein on three manifold is known or at least expected doesn't satisfy gluing property? Do you expect it to fix that or?
So I mean, my take is that normal skein modules of three manifolds satisfy some gluing property, but you have to be very careful about what you assign to the part of the boundary surface where you glue along. So then you can make gluing statements.
Another question is, so in this Infinity 2 category of circle bimodules, do you say explicitly this triply graded invariance is evaluated on some three manifold on the sphere and with some knot boundary? I don't know. So
not directly in some sense. So the mechanism that gives rise to triply graded homology is a bit artificial. It's you take this chain complex of circle bimodules, and then independently of that being a chain complex, you compute Hochschild homology termwise.
Yes.
And then you compute homology of the resulting chain complex. So it really naturally appears as some filtered object. It somehow it's defined as living on an E2 page of a spectral sequence. So that seems to be important, but I don't directly see how this now appears as evaluation of some manifold invariant, for example. I mean, it certainly has the characteristic of some trace-like operation, but I don't have a direct TFT interpretation. So in some sense, all these bi-graded theories feel a bit more natural in that setting because there I can say it's just the invariant of the four ball with its given boundary condition.
Thank you.
Thank you for this very nice talk and interesting talk. You mentioned that this invariant is computable in the sense that if you have some relations, then you can. But thinking, for example, in the Reshetik in Turaev, it already, even the UQSL2 with a small root of the unit, you can encode problems that are NP complete. So my question is, if you know that in this case happened the same, that let's say that you can encode some problem and the complexity of the problem grows.
Yeah, no, it's even worse than that. It's even worse than that because typically, even to compute the invariant of a two-handle body with consisting of a single zero handle and a single two handle, you need to do a countable number of computations. You basically need to know all the colored Kavanagh homologies of the attaching knot. So this should be a finite problem. In analogy to the fact that color-Jones polynomials are Q-holonomic. So the sequence of color-Jones polynomials of a fixed-frame knot carries only a finite amount of information. We expect that something similar is true for the colored Kavanagh homologies, but at the moment, don't know how to access, how to prove such a thing or how to access this. So at the moment, it says you have to compute a countable number of Kavanagh homologies, and then they have to be patched together as some colimit, so quotient of a direct sum. So computable is to be understood in this sense. So it's a recipe for what you have to do to reduce to link homology computation in the 3-sphere, but it will typically not be a finite computation. Problem for maybe students out there, if you can prove that the skein module is locally finite dimensional, so finite dimensional each degree, then you have some hope that there could be an approximation scheme, that in a fixed degree you could compute the invariant in that fixed degree through some finite computation. But at the moment we don't even have that, because we don't understand when this thing is finite dimensional and when not.
Thank you.
In the categorization of the trivial and receding trive theory, so I think for trivial and receding trive theory, they have some asymptotic behavior, right? They are some quantization of the transassignments. So in the categorification picture, do you also see such asymptotic behavior?
I'm not sure I understand the question fully. Yeah, so that's a fantastic question and a great motivation to look into this further, but I don't have anything to say right now, unfortunately. Maybe what I should emphasize is that we cannot categorify Reshtig and derive yet. Don't have a boundary theory in some concrete description yet. Yeah.
Is there another one? Okay, let's thank Professor Wedrich again.